Hey guys, today we're going to be doing the cone problem. This is just another related rates problem. I'm going to be going over it in depth and explaining it and how to go about it. And just, showing you guys something a little different because the cone problem requires a few extra steps compared to what we've seen, in the ladder problem. And I think there was another one I posted before that. But yes, the sphere problem. It requires a little more, so let's get into it. Just gonna get my pen. So, what do we have here? Well, a water tank takes on the shape of an inverted circular cone, with a base radius of 3 meters and a height of 5 meters. If the water is being pumped into the tank from the top at 2 cubic meters per second, what rate is the water rising at when the water is 3 meters deep? So that's a lot to take in. That's a lot of information, a lot of numbers. Got like 4 different numbers, 4 different values. And, we gotta visualize what's going on here. And the best thing to do right at the start of any related rates problem is to draw the situation. So let's do that. Usually I should use a bigger, there we go. So we got an inverted cone. Actually, I'm gonna back up a second. So usually you say cone takes on this shape, and an inverted cone would be this, but flipped upside down. So there we go. An inverted cone. I'll draw that better. Drawing skills are not at the peak today. Okay, there we go. So we have an inverted cone. This is our water tank. So the base of this tank has a radius of 3 meters. And looking at this picture, this is the base. This top flat area, the circular area, this is the base. And it has a radius of 3 meters. And this entire cone has a height of 5 meters. Water is being pumped into the tank at 2 cubic meters per second. So water's coming, we got the spout here. Water's coming into this tank down at 2 cubic meters per second. So that immediately we know that is our change in volume. Now the question is, how fast is the water rising when the water is 3 meters deep in the tank? So somewhere here in the height, the water is 3 meters deep. We got 3 meters. What we want to know is how fast is the height changing? How fast is the water rising when the water in the tank itself is 3 meters deep? Now, in every related rates problem, we need to relate one of the rates to the one we're interested in. Now, currently, we know how fast the volume is changing. And we want to relate that to how fast the height is changing, and we need a relationship to do so. So, well, what is a great relationship that relates volume and height? The two things that we're looking for, the rates. Well, obviously, the volume of a cone. The equation for the volume of a cone is a great place to start. So what is the equation of a volume of a cone? You can look this up anywhere, basically. It's V is equal to 1/3 pi r squared h. Now, this is just something, I guess you just should know from previous math classes, I guess. For me, it's rarely been given on tests. It's just that you expect you just know it. It may work different in different places. Ask your professors if you know need to memorize different types of shapes, like like the volume of a pyramid or something like that. Something a little more not as common as something like a sphere or a cube. So just make sure you clear that up with your professor if you need to memorize these formulas for tests, or just know them. So, well, now we have a relationship between volume and height. And, well, let's take the derivative with respect to time of this equation. And I'm going to show you a very common mistake. Students will take the derivative of this right away because they found a relation and they're going to start taking the derivative with respect to time. And they're going to run into a problem. There's two types of mistakes. The first mistake is that students do this. This is wrong because you ignored R. R is also changing. As the amount of water in the tank changes, the radius is also changing. As more water is being put into the tank, the radius is also changing with respect to time. And students do not treat, R as something that's changing with respect to time. They don't treat it like that. And therefore, R is not a constant. It's not some constant value. So you need to realize that it also depends on time. So in this equation, you have two variables that both depend on time. As the water is being pumped in, both the height and the radius are changing. Because obviously the water is rising, as I'll depict right here. The water is rising. The radius here of water up here is different than the radius here. So as the water rises, the radius will also change. So we need to be aware of that. That is the first mistake. The second mistake students make is they realize that, that R is also changing as more water is being pumped into the tank. And they take the derivative and they get, 2R times dr by dt, h, and then take the derivative of the second variable, take the derivative of height, and they get something like this, and then they're stuck because, well, they don't know this. And they still got to figure this out. They don't know this either. It's not given. And these are two common mistakes students do. They either don't realize that R is also changing with respect to time, or they completely ignore it, or they do realize and they take the derivative like this. How we do in other questions. We find a relationship and we just take the derivative right off the bat with respect to time, and we get this relationship. But here's the thing. In previous questions, we only had, one thing that depended on time. Here we have two. We both R and H depend on time. So what do we do here then? We're stuck. Our old approach doesn't exactly work. So, well, let's look at what we're given more closely. We're given this cone. I'm going to draw it again. It's got 3 meters is the base radius. It has a height of 5 meters. And we want to find how fast the height is rising when the depth of the water is 3 meters. So this is 3 meters. Well, if you take a cross-section of this cone, what we find is a triangle. Cross-section. So 3, 5, and we have another triangle within it, which has also got a height of 3, right? We have similar triangles here. These triangles have the same ratio between both of the side lengths. So we can actually exploit that. R over H. What is the ratio of the radius over the height? dealing with, the entire cone, not the part where I'm saying, the depth is 3 meters. Well, the ratio between these is 3 meters over 5 meters, correct? Well, we can exploit this and we can say, well, since we don't know R and we don't know dr by dt, and we have, two different quantities we're looking for, and we're looking for dh by dt, what we can do is we can say R is equal to 3 over 5 h. And we can substitute this equation into our original equation, our volume equation. By doing this, we effectively just rewrote the radius in terms of the height, and therefore eliminated the radius factor out and just replaced it, with its equivalent, but in terms of height. Therefore, we only have one variable on the right side of the equation to deal with, and that makes it much, much more straightforward. And this is basically the key to the cone problem, is to realize that there's this similar triangle relationship that you can exploit, and this ratio that you can use. So let's do this. So what was it? Well, R over H is 3 over 5. So R is going to be 3 over 5H. So we get 3 over 5H. Don't forget it's squared times H. Next, well, let's clean this up. 1 over 3 pi. We got 9 over 25 H cubed. So there we go. And now we can actually just gonna clean this up a little more. Volume is just 9 over 75 pi h cubed. And I'm just gonna erase everything we have up here. Get rid of all this, and we are going to take the derivative with respect to time of this equation. So what do we have? Well, we have dv by dt, which is given to us in the question, is 2 cubic meters per second. And let's take the derivative. Well, we got 9 over 75 pi times, using the power rule, h squared times dh by dt. There we go. So now it's just a matter of just substituting in values. And so we know what dv by dt is. It's given to us. It's 2. And, well, these simplify down to just 9 over 25 pi. And h, well, we want to know how fast the water is rising when the water is 3 meters deep. So that's 3 squared. And we're looking for dh by dt, how fast the water is rising. So I'm going to erase this. So it's just a matter of now just computation, and, well, this is just 1 pi times dh by dt, and this just comes out to 50 over 81 pi meters per second, I guess. dh by dt. This is our final answer. So here we go. We got our final answer. 50 over 81 pi meters per second. That's how fast the water is rising when the water is 3 meters deep in the tank. And there we go, we got our answer. And the key to this problem is just, exploiting that relationship, because doing it the way that we, worked out the sphere problem, which is also something that dealt with, a tank that was filled with water, that was a balloon actually, being filled with air. You can't directly just go, start taking the derivative right when you get the relationship with respect to time, because you run into kind of a dead end. And when you run into a dead end, you need to look for other relationships to exploit. So usually you're looking for a way to write, for instance, we have two variables here. We have the radius and the height. You're looking for some way, some relationship to exploit where you could rewrite one in terms of the other, therefore effectively eliminating one of them. And that is important. And that's not just important for the cone problem, that's important for a lot of different related rates problems. So I said this in my first related rates video, is that I don't want to have you guys memorizing how to do these questions. It's more, getting that general idea of how to work through these. And this is probably the first one where we've seen we have to exploit some other relationship, and usually when you run into a dead end, always look for some other relationship, look for some way that you could rewrite one of the variables in the question in terms of the other. And this way you can effectively, finish the question. So thanks for watching. I hope you guys learned something from this, and like and subscribe.